So if you read the question, it says, moon of mass m orbits a planet of mass 49m in an elliptical orbit is shown. When the moon is at point A, its distance from the center of the planet is RA and the speed is v0. When the moon is at point B, the speed is 5v0. Fine, we all got that. Now it says, when the moon is at point A, the distance from the moon to the center of the planet-moon system is most nearly. So this is a center of mass question, which was not obvious to me the first time I read it, mostly because I interpreted it as going to be something else. So let's do the center of mass real quick. Remember, when you want to find the center of mass, you take m1 x1 plus m2 x2 all divided by m1 plus m2. Now that's when you only have two objects, right? No big one. You can put the 0 wherever you want it to be. But because they're asking for the center of mass from this here, I think if you put the 0 right here, it makes it easy. Because the center of mass is going to be somewhere between these two, correct?
Mm-hmm.
It's got to be somewhere in there. Let's say it's here or whatever. So if I want to find the position of the center of mass, I'm going to take m1, which is m times position 0, plus 49m times RA, all divided by m plus 49m. And so what you end up with is 49 MRA on the top and 50m on the bottom, so 49 over 50 RA. So that means that the center of mass is all the way over here at 49 out of 50 from the of RA. Is that cool?
Mm-hmm.
So this was a center of mass problem, kind of hiding in a planetary motion assessment. So things like that happen. All right, that was that one.
That's the one you just did.
That was it. So that's 17. That's a question I just answered. What about 18? So it says, now this is 18. It says, when the moon is at point B, so now we're here, the distance from the moon to the center of the planet is most nearly. So now, now what we're looking at here is we're saying like, okay, so given this situation here, we want to find this distance here. Okay, we want to find that distance there, right? So, how are we going to do that? Well, I think this is where we're going to have to use our our angular momentum. Okay, we're going to have to use our angular momentum. So, at these 2 points, I know the angular momentum is conserved. So L at point A is equal to L at point B. Angular momentum, you can find it a couple different ways. You can do R cross P, which is RMV sine theta, which in this case is just RMV. Or you could use angular momentum as I omega. Planets are point masses, so point mass is mr squared, and omega is v over r. Either way, we end up with RMV. So RA m v at A is equal to R at B m v at B. Is that cool? So RAVA equals RBVB. And what I know is that the V at B is 5 times the V at A. Is that cool?
Uh-huh.
And so if I substitute that in here, we can see that R at B is 1/5. our day. And again, this is something we talked about the other day, that if you are 5 times as far away from the planet, or from whatever you're orbiting, you're 5 times as slow. That's a cool thing. Yes?
Would the VAs cancel? And then it would be RA over 5?
Yeah, first.
Alright.
Okay, that was 18. Let's look at 19. What is it going? So it says, a comet moves in the sun's gravitational field following the path shown. What happens to the angular momentum as it moves from point A, or point X to point Y? What do you think is going to happen to its angular momentum?
Remain constant.
Stays the same, right? An easy one. I think that's the answer. Remains constant. Whew, that was a close one. All right. So this one's a little dicey. So I really want you guys to focus on this one. All right? So this one says, a rocket landed on planet X, which has half the radius of Earth. That's going to be important. An astronaut on board the rocket weighs twice as much on X as he does on Earth. That's giving you a sense of the gravitational field strength. If the escape velocity for the rocket taking off is v0, then the escape velocity for planet X is. All right. So, there's a lot going on here. Let me do the basic principles again so that you can see where they're coming from. Okay? We know that the local gravitational force is equal to the universal gravitational force. So this is at the surface, correct? This is at the surface. So my g value is going to be equal to gm all over r squared. So this is the acceleration due to gravity, or the gravitational field strength. They're just assuming you know that those two things are conceptually different but mathematically the same. R is the distance from the center, and if you're on a planet, that would be the radius of the planet. This is the mass of the planet, that is the universal gravitational constant. Is that cool? So for Earth, g for Earth is equal to g times the mass of Earth all over the radius of the Earth squared. Is that cool? Now, we talked the other day about escape velocity. So if you're on a planet, and you're going to throw a ball so hard that it's going to go out to infinity, slowing down the whole time. When you get to infinity, r, your distance, is going to be infinity, and it slows down the whole way, so your velocity is 0. Is that cool? So this is the escape velocity. This is the escape velocity condition, that you're slowing down to infinity, and when you get to infinity, that's when you stop. Now, infinity is not a place. Don't get excited. What this means, though, is that if you look at your gravitation, your universal gravitational equation, kinetic energy is 1/2 mv squared. What is the universal gravitational potential energy equation? In your homework, some of you just threw in mgh here, because mgh is the potential energy, the gravitational potential energy at the surface of a planet. But as soon as you get off the surface of a planet, or far enough away that the radius matters, we have to use a different equation. So it's negative g big M little m all over r. Now, what I like about this is if I want to find the total mechanical energy, I'm going to do U plus K. I'm feeling pretty good about this. But what do I notice in this situation? If I'm at infinity, my velocity is 0, so what's my K value?
0.
0. And if I'm approaching infinity and I put infinity in here for r, what happens when you start putting really, really, really big numbers in the bottom of a fraction? It goes to 0, right? And so we end up with 0 plus 0, so the total mechanical energy is equal to 0. Here's the thing. As soon as you throw it, There's no more energy added or taken away from it. It's just changed from kinetic to gravitational potential. Therefore, when I look here, I know that my E initial is equal to my E final. But what is my E final? 0. And now I'm talking about, well, what was my E initial? Well, it was the U plus K at the surface. So, U is negative GMM all over R, because I was at the surface when I threw it, plus 1/2 mv squared. But this is equal to 0, correct? If this is equal to 0, if I add this term to both sides, I end up with this expression, 1/2 mv squared is equal to G, big M, little m, all over R. We can see that the mass of the object is going to cancel, so the mass of the object doesn't matter. I mean, it would be harder to throw it. You'd have to apply more force to get it to go that speed, but the speed is what we're looking for. So V squared is equal to 2 big G, big M, all over R. Therefore, V is equal to the square root of 2gm all over R. And this is the escape velocity. All right, you guys got that? This is something that you'll need to be able to understand. Now, here's the thing I think is super cool about this, is this is the acceleration due to gravity on a planet. This is the expression for escape velocity. Do you see how some of the same letters are coming together in these? So I want to write my escape velocity in terms of acceleration due to gravity. How cool would that be if I could put those two things into one idea? Okay? So let's look. I'm looking at my G over here. G is equal to big G, big M, all over R squared. But when I look here, I have GM over R, correct? So what I'm going to do is I'm going to multiply both sides by R. So on this side I have RG, and this side I have GM over R squared times R. So I multiply both sides by R. See how sneaky that is? Now look what happens, because this is super cool. One of these R's is going to magically disappear, and I end up with RG is equal to GM over R, which is this thing here. You see it right here? See that? So then how am I going to write my escape velocity then? How about 2RG? See how interesting that is? Well, it's interesting to me. I find it fascinating. I like the fact that, you can write an equation for something in terms of something else, which I think is really cool. All right, so that's that. All right, now let's look at the problem itself. We've done the framework for it. All right, what's the problem say? A rocket landed on a planet which says half the radius of Earth. All right, so Rx is equal to R Earth. Okay, that sounds good. And then an astronaut weighs twice as much on X as he does on Earth. What does that tell me?
2 times the G.
Yeah. That's exactly what it tells me. Is that cool? And so now we're almost done with this problem. We got to this point here. We got to that point there, which was important. And let's see how it manifests now. So if I write the escape velocity for Earth, it's equal to square root of 2 RG, R Earth, G Earth, And the escape velocity from x is equal to the square root of 2rx gx. Well, now I'm going to rewrite this here. So this is 2. Rx is re over 2. And gx is 2 g earth. And look what happens. Two REGE. So this is our escape velocity for x. How does it compare for our escape velocity for Earth? Well, look, they're the same. Is that cool? So what I like is, even if you look at this equation here, it says that the radius of x is half that of Earth, but the gravitational field strength is twice. So these are both linear relationships here, so if you divide one by 2 and multiply the other by 2, they cancel there. So I found that one a little hard. Okay? I will say that problem is actually a little bit challenging. One more. Oh, was that it? Is that 20? Perfect. Okay. Excellent. All right. If you didn't do quiz A last night, please do it tonight. Okay, please do it tonight. Because I would like to go over it, but I can't wait. Like, I can't wait for you guys to catch up. All right? So please do it tonight if you haven't done it. Look like an elephant. All right. Crucial piece of information. I'm working on my salmon ladder and I'm very sore because of it. Ugh. All right, here we go. Fine. So annoying. So what we do in physics is we have an idea, okay, that we're familiar with. So I'm going to take an object, I'm going to hang it on a string here, thusly. Adjust the height of this one so they match. Lost your car. That's pretty good. All right. So in the physics class, when we take an object and we put it on the end of a string and we swing it, what do we call that thing?